This presentation will discuss how to compute the specular component of light in the PhongLighting model. As we've discussed in earlier presentations, the light as seen by the viewer, I, is computed as with four components: the ambient component, IA, the diffuse component, ID, the specular component, IS, and the emissive component, IE. We've already talked about how to work with the ambient, diffuse, and emissive components. In this talk, we'll cover the specular component. And this is doing the basic PhongLighting computation for this. So then in the setting for specular lighting, we've got a surface S with a point X on it, normal vector N, a light here, and light is shining in, I'll use a towards the point with a vector L that's univector pointing from X towards the light. So the light's coming in. I'll shift to red color momentarily. So there's a bunch of light coming in here towards the point X, and it reflects off in mostly the direction of perfect reflection. So we think of the light as hitting the point X and then reflecting off, but in much less brightness as you get away from the direction of perfect reflection. So the direction of perfect reflection I can draw on here as another unit vector, R, and R is the direction of perfect or mirror-like reflection. So to redraw this with all the vectors shown, here's the same scene. I've got X, I've got the normal vector N, I've got the L vector pointing towards the light, I've got the vector towards the viewer, which is the V vector, and then I've got the direction of perfect reflection, which I call R. And this R, let me draw it a little more symmetrically, it's a unit vector just like L is. All these vectors are supposed to be unit vectors. And it makes the same angle theta with the normal vector that L does. And we now also call this angle between R and V phi. So this is the picture here. These may not all be coplanar vectors, but certainly L and N and R are because they're reflecting across each other. So for the first part of the computation, let's discuss how to compute the direction of perfect reflection R. So the formula for R is the following. R is equal to 2 times L dot N times N minus L. So let's get a picture that shows this. So here is the point X down here at the bottom of the board. Here's N. Here's L. Here's R. And let's consider the projection of L onto N. And that'll, by symmetry, that'll also be the projection of R onto N. So this vector here is the projection of L onto N. And I'll give that a name U just for the moment. So U is equal to L dot N times N. This works because N is a unit vector, and so we don't have to worry about dividing by the length of N here. So we take the component of L along the unit vector N times the unit vector N, and that gives us the vector U. And then we notice that L minus U, that's this dotted vector coming from U to L, by symmetry, is equal to U minus R. That's the vector from R to U. So from that we get immediately that R equals 2U minus L, and that's equal to 2L dot N times N minus L, proving the formula for R. Next, we can give the formula for I sub s. This is the formula used typically in PhongLighting. So I sub s is equal to rho sub s. That's the specular reflectivity coefficient times, here's a new factor, cosine of phi to the f times I in s. So this is the incoming light, I in s. I is the light heading towards the eye. And the specular reflectivity is the fraction of incoming specular light that's reflected. The cosine of phi to the f gives us the specular highlight. So the idea is the following, is that cosine of phi to the f should be close to 1 if phi is approximately 0 or close to 0, meaning that the reflection direction, r, is approximately equal to the vector towards the viewer, v. So if the reflection direction and the viewer direction are the same, that's the direction of maximum specular light reflection. If they're very close to each other, should also be close to 1. But the minute that angle phi gets bigger, the view direction is different by a fair margin from the reflection direction, then the specular reflection should drop rapidly to 0. And this is in order to get this effect where we get small specular exponents, small specular highlights on objects, so that you only see the specular light reflected from a small region on the surface. So let's take a look at what this looks like. So here, f is the specular exponent, also called the shininess coefficient. And typically this is going to be some number, say between 10 and 200. A small number like 10 would be very broad specular highlights. A number like 100 or 200 would be much narrower specular highlights. And depending on your scene and your application, you pick this number by hand to look decent. Okay, and this is a material property. In other words, it's a property of the material that's coating the surface. So if you have a glossy surface, f would be big. If you have a very matte, non-glossy surface, f would be very small, and maybe also rho sub s would be small. So let's see what this looks like. Let's graph what cosine of phi to the f looks like. So first of all, phi is, let's think of phi being in the range 0 to pi over 2. So for now, we have to make an adjustment to the above formula if phi is not in that range. But for now, let's think of phi in that range here. So here's our cosine function, cosine of phi, and that's like cosine of phi to the 1, right? If we take cosine of phi squared, it's going to look something like this. This would be, the first one would be f equals 1, here's with f equals 2. If we took f equals 50, cosine of phi to the 50 is going to look more or less like this. So what happens is as f gets bigger, the cosine function turns into something that's very close to 1 at phi equals 0. Think of this as the phi axis there, and drops rapidly to 0. If f is small, then the cosine function, cosine phi to the f, is a broader function, allowing reflection to spread out over a wider range. And so this is how the f function controls the size of the specular highlight. Now, this involves a trig function. We'd like to avoid that, so we can actually simplify this by saying this is the same thing as Vs times R dot V, to the f times I in S. And this is the formula that would typically be used for the Phong calculation, but it only works when cosine of phi is between 0 and pi halves. It's possible that if phi is greater than pi halves, then cosine of phi is less than 0 and r dot v is less than 0. This is not what we want to do, because in particular, if f is a floating point number, raising to a negative number to an exponent is questionable. But also, what it means in the picture here, if phi is bigger than pi halves, it means that the reflection angle is pointing away from the viewer. Instead of being on the same side close to the viewer, it's more than angle 90 degrees away from the viewer. So the direction of perfect reflection is way away from the viewer direction, in which case we should just set I sub s equal to 0. In this case, we set I sub s equal to 0. We can put this into a single formula as the following: Is equals rho s times the maximum of 0 and r dot v raised to the power f times I in S. So this formula in the box is our official formula for IS in the original formulation of the PhongLighting model. There are other ways to compute this, and I'll talk about a very popular way, the halfway vector method, on the next board. Now we'll talk about the halfway vector method for computing specular light. So we're going to define a different vector than the r vector to work with. Namely, we're going to take the average of the direction to the light, L, and the direction to the viewer, V, and we'll call the resulting vector H for halfway. So let's draw a picture of this. Here's X, here's the normal vector, here's the direct vector towards the light, here's the director towards the viewer. And if we go halfway between these two things, so we think of right in the middle, this will be the halfway vector H. So these two angles are the same here. And the formula for H can be, so that we can take L plus V divided by the magnitude of L plus V. And that will be a unit vector because we divided it by the magnitude of L plus V. And L plus V will be sitting up about here. We normalize it to get H as L plus V. And the idea is the following, is that this angle here, which I'll call psi, we have that psi is approximately equal to phi over 2. Actually, it's exactly equal to that if L and N and V are coplanar. If they all lie in a single plane. And we're mostly interested in the case where they're coplanar, or, well, more correctly speaking, close to coplanar. The reason being that if they're not close to coplanar, then the angle phi and the angle psi are both going to be big, and there won't be much specular reflection at all. In that case, we don't really care that much about the specular reflection because there won't be any to speak of. There won't be any visible. So we can just, for the purposes of thinking about the halfway vector, we just think of the vector psi as about half of the vector phi. And then the formula and the intuition here is that H is close to the vector n if and only if It's just an intuition, and I'm just not defining exact close to means. If and only if v is close to the vector r, and that's if and only if psi is small, and that's if and only if phi is small. And these are the cases where there's some noticeable specular highlight. So, and in this case, I sub s is non-zero, right? So there's some reflection going on. So the formula that we use, so the new formula, the halfway vector formula for IS 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 equals rho s times cosine of psi to the f times I in s, and that's the same thing as rho s times h dot n to the f times I in s. And this is the formula we would typically use to avoid the use of trig functions. So there's several advantages to the halfway vector, which I'll squeeze into the bottom of the board here. So advantages. So one advantage is that h dot n is always greater than 0, greater than or equal to 0 at least, and we don't need to therefore do that max stuff anymore. So h dot n is greater than or equal to 0. Why is it greater than or equal to 0? Because they're both pointing upward from the surface. We're always assuming that the light is above the surface and the viewer is above the surface. Otherwise, we would just skip the computation completely. So h dot n is greater than or equal to 0, so we don't need the max 0 dot 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 term. We don't have to check whether it's less than 0, just because it's always greater than or equal to 0. Another slightly strange advantage is that if f is less than 1, we avoid a abrupt change in illumination levels. In this, actually, it's a change in the derivative of the illumination levels, but I'll just write it this way. In illumination levels that happens in the earlier case when theta was exactly 90 degrees. So that's another advantage. This is a somewhat strange advantage, to be honest, because f less than 1 is not really the intended use of specular highlights. That would be giving you a huge specular highlight, which would not be a traditional specular highlight. The other advantage is that sometimes, this is an old advantage that I would say it's not so commonly important nowadays, is if you can take L and V to be constants. So if we could take the L vector and the V vector as constant throughout the whole scene, and then H is fixed too. And then, so that saves computation of H. Saves the computation time to find H. Now, this is a somewhat old-fashioned advantage because people actually do so much computing nowadays. Graphics processing units and shaders are so powerful that a computation of H is not a big deal anymore. But it is one of the reasons it was originally introduced. What would it mean for the L to be constant throughout the whole scene? It would say that the light is shining at every point X from the same direction. And that happens, or approximately, if the light source is very far away from the scene. And in this case, that would be called a directional light. So a directional light would be a light that's shining at the same direction at every point. So every point has the same L vector, even though they're at different points in space. And it's as if the light was shining in, say, from infinity, and there's a big beam of light coming in at a constant direction. The V being constant is a little less physically realistic. Sort of means that no matter what you're looking at it from the same direction. This would be true approximately if the viewer was a great distance from the scene and looking in at the scene, say from a telescope. And so it would be like the point of view of the viewer would be the same for every point. So, but again, that's a little less realistic because usually our viewers are sitting in the scene. We have some perspective. We want to see that perspective. And so therefore, nonetheless, H vector is widely used, and if nothing else, just for reason one, it saves a little bit of checking for whether or not something is less than or equal to 0. So that's the computation of the I sub S for PhongLighting, and end of this presentation. Thank you very much.